data quality. So whatever data is collected for some other purpose, if we try to use that for data mining applications, obviously it will have some disadvantages. So we should address some quality issues from at the source, and we have the following. These are the examples of data quality problems, whatever is available, that is noise and outliers, missing values, duplicate data, and wrong data. And variety of problems will be there with that involve measurement error like noise and artifacts, bias, precision, and accuracy. So measurement and data collection errors, they may ask you these terms. The term measurement error refers to any problem resulting from the measurement process. So the common problem here will be that the value recorded will differ from the true value to some extent. So that's an error, isn't it? If there is slight change also, we say there is an error. And for continuous attributes and this numerical difference of the measured and true value is called the error. And the term data collection error will refer to errors such as some data objects may be omitted, or some attribute values may be omitted, or we could have some inappropriate, or inappropriately we could have included a data object. Those are all termed as data collection errors. Maybe some definitions they'll ask. Let's look into the question paper, then we'll get some idea what will be asked from these topics. And noise, as you know, it's a random component of a measurement error, and it's nothing but a distortion of value or addition of some spurious objects. And this is an example for it. This is your time series before the noise, and after addition of noise, see the disturbances. So it has been disrupted by some random noise. And this is one more example which shows set of data points before and after some noise points, and that is indicated by this plus. So indicate the appearance of plus will indicate that a noise has been added. Okay, so we'll have here we have noise as well as the non-noise points both together with noise points plus added. See here we have some noise added, and these are three groups we have. And after the after noise is added, it looks like this. Okay, and so noise is often used in connection with data that has spatial or temporal component. So we use techniques like signal or image processing to reduce noise, and we also try to discover patterns that might be lost in the noise, because when noise is added, some patterns may be lost. Hence, we try to discover those patterns also. And elimination of this noise is frequently difficult, and we have some robust algorithm in data mining which focus on these, which will try to produce acceptable results even when noise is present. Okay, so we have some robust algorithms in data mining which try to produce acceptable results even when noise is present. And data errors may be the result of more deterministic phenomena, such as a streak in some place on a set of photographs, and such deterministic distortions are often referred to as artifacts. So artifact means there is some distortion, usually on a set of photographs and some things like that. Those those will constitute to artifacts. And precision, bias, and accuracy. And these are the definitions of precision, bias, and accuracy. So in statistics and experimental science, the quality of measurement process and the resulting data will usually be measured by this precision and bias. So what is precision? The closeness of repeated measurements of the same quantity to one another. When you try to repeatedly measure something, there will be some difference of the same quantity. We may get at each time we may get some difference. So that is precision. And bias, a systematic variation of measurements from the quantity being measured. There will be a variation in the measurement from the quantity which is being measured. And accuracy is the closeness of measurement to the true value of the quantity being measured. So we can say that, oh, our product is this much accurate. So there will be some fixed quantity, and we will just try to have show the closeness with that. So closeness of measurement to the true quality of the quantity being measured. So that is accuracy. And outliers, they are either data objects which have characteristics that are different from most of the other data objects in the data set. So they will be different, or they can also be values of an attribute that are unusual with respect to the typical values for that attribute. Like there is some value which is expected for that particular attribute, but this is different from that or unusual from the expected value. So that we can call it as outliers. And unlike noise, these outliers will be of interest. We will have interest in finding these outliers. Okay, so moving on to 2.3, data processing. These are some of the issues of which pre-processing steps should be applied to make the data more suitable for data mining, because as we discussed, the data may be collected for some other purpose. If we try to use it for data mining, then we need to address the issue of which pre-processing steps should be address these issues on which we have to apply the pre-processing steps. So aggregation, sampling, dimensionality reduction, feature subset selection, feature creation, discretization and binarization, and variable transformation or attribute transformation. Both are one and the same. Attribute, variable, all are one and the same. So these are some of the pre-processing steps. Into one by one. Sorry. Aggregation is nothing but we combine two or more attributes or objects into a single attribute. So sometimes, yes, we combine we just combine two or more attributes into a single attribute. That is nothing but aggregation. And the purpose of this is for data reduction, where we reduce the number of attributes, isn't it? When we have more attributes, we try to combine two or more attributes so that we can reduce the number of attributes. So the purpose of aggregation will be data reduction or change of scale. That is, it is aggregated into regions and we have states, countries, etc. Change of scale. And these examples you know very well. In beginning data warehousing we have discussed. Days will aggregate into weeks, then months or years, and more stable data aggregated and as change of scale and more stable data to get more stable data. That is aggregated data tends to have less variability. Hence we try to find more stable data by using this aggregation. So aggregation is nothing but combining two or more attributes into a single, and the purpose of which will be just to reduce the data. That is, when we combine the number of attributes, we will reduce the data, and change of scale where we can aggregate like this, and also to get from the year 1982 to 1993. What precipitation in Australia is done. So it shows a histogram. In the next slide, we have a histogram for this standard deviation of average monthly precipitation, that is 3. So we have this. To check this, we can use this aggregation. So that this is the inference what is derived easily done by using this aggregation. So average yearly precipitation has less variability than the average monthly precipitation. If you look into this, this has less variability than this average. So, and these measurements are also in centimeters. So for this use, we can have this aggregation being done. Okay. subset of the data objects which needs to be analyzed. And usually in statistics, it has been used from long time for both the preliminary investigation of the data and also the final data analysis. Okay, it is one of the techniques which is used for data reduction, and in statistics it is used for both preliminary investigation of the data and the final data analysis, and it's very useful in data mining. But sampling in statistics and data mining will usually be different. They're not same, because in statistics they usually obtain the entire set of data of interest, which is too expensive or time consuming. If we consider the same thing for data miners, it becomes too expensive or too consuming to process all the data, because you know that data mining means we have a huge amount of data. And in such a case, we use sampling algorithm, which can just reduce the data size to a point where you can get a better result you can get, but you should have to use more expensive algorithm for that. And the key principle for this effective sampling is these two. That is, we use using a sample will work almost as well as using the entire data set if the sample is representative. And what is representative? A sample is representative if it has approximately the same properties as the original set of data. So we have some original set of data, from that we select some sample, and this sample will be having the same properties as the original data set. So instead of working on the whole data set, you can just take a sample and work on it. So that is a key principle for effective sampling. And these are some of the samples whatever is taken. So this, if you take 500 points, this sample looks like this. If 2000 points are considered, then the sample looks like this. And if 8000 points, the sample is different. As you increase the number of samples, you can get good results. So once a sampling technique has been selected, okay, we have these different. So once the sampling technique has been selected, you also have to just choose. So what are the types of sampling? Let us see first, then we can say take that example. So we have simple random sampling, sampling with replacement, and stratified sampling. These are the three types of sampling we have. So there is an equal property of selecting any particular item in simple random sampling, and sampling without replacement. As each item is selected, it is removed from the population. And sampling with replacement is objects are not removed from the population as they are selected for the sample. Here we will remove it, whereas here we are not. In sampling with replacement, the same object can be picked up more than once. So sampling with replacement is that, because we will not remove it from the sample, it's obvious that it can be picked up more than once. And stratified sampling is we split the data into several partitions, then draw random samples from each partition. So we have these three types of sampling: simple random, sampling without replacement, with replacement, and simple and stratified are the two types. Under this we have these two, and stratified is this. So what sample? So this is an example for that. So once this sampling technique has been selected, like whether it is simple or stratified, it becomes necessary to choose a sample size, because larger sample size will increase the probability that a sample will be representative, but also eliminate much of the advantage of sampling. On the other hand, with simple sample size, pattern may be missed, or you can have erroneous patterns which will be detected. So this is an example where, as I said, this is a sample set with 8,000 and other two are with data size 2,500 points. So here also we can see that most of the structure of this data set is present in the sample. But here most of it is present if we will compare. But here most of it is missing. So it becomes very much necessary to determine the proper sample size. Okay, sample size becomes very much necessary because we may end up in missing some of the patterns if the sample size is not properly selected. Are you all listening, or I'm just talking to myself? People are there.
Listening, ma'am.
Okay then. It'll be boring only, but it's okay. You can catch some points from all these things. So if at all, if we have this is an example. So it's a probability of a sample that contains points from each of 10 groups. So this shows the probability of getting one object from each of 10 groups, that is 10 to 60. See, 10 groups, 10 to 60. So with a sample size of this 20, if we will take the sample size as 20, we have 20% there is little chance, that is 20% of getting a sample that includes all 10 clusters. And with sample size of 30, we have a moderate chance. So this is an issue which will further be, we will be discussing in the context of clustering, where we will discuss those things later. So what should be the sample size which needs to be selected? If the sample size is more, we will have a less chance of getting a good result. So let's look into those things later. So we have two types of sampling: simple random sampling, under which we have again two more types: sampling without replacement, with replacement, and stratified sampling. And we have progressive sampling. This it becomes difficult to determine the proper sample size, isn't it? So adaptive or progressive sampling schemes are sometimes used. And what are these? These approaches will start with small sample size and then increase the sample size until sample of sufficient size has been obtained. This technique will eliminate the need to determine the correct sample size initially, but it requires that there be a way to evaluate the sample to judge if it is large enough, isn't it? We cannot simply keep on increasing the size of the sample. We should also have somebody should be able to judge, like something should we should stop selecting the sample size. So it requires that there be a way to evaluate the sample to judge if it is large enough. So that is not there in this. So we have dimensionality reduction. So this is dimensional reduction means if a particular record has, if a particular database or whatever has more number of dimensions, then they should be reduced. So data sets sometimes can have a large number of features. So in that case, if at all, if assume that we have dimensions in thousands or tens of thousands of attributes. So in that case, we have to just reduce the dimensions. And there are variety of benefits to dimensionality reduction. So what do we do to reduce? I lost the connection, I guess. So reduction of dimensionality, we do it by selecting new attributes which are nothing but subset of the old one, and this is known as Am I audible now? So the reduction of dimensionality by selecting new attributes. These new attributes are nothing but subset of the old, is known as feature subset selection or feature selection. So that is also one more thing, isn't it? Feature selection we discussed in the beginning for data processing. Feature selection or feature subset selection is important. And curves of dimensionality and dimensionality reduction techniques will usually be based on linear algebra approaches like principal component analysis. And dimensionality reduction, as I said, it's nothing but reducing the number of dimensions or attributes. And it's nothing but we will have combination of old attributes. So curves of dimensionality, it's a phenomena wherein many types of data analysis become significantly harder as the dimensionality of the data increases. So in a data set, you can have thousands and 10,000s dimensions. In that case, when you go for data analysis, then it becomes very hard to, as the dimensionality of the data increases. So that is called as curves of dimensionality. And usually the data becomes increasingly sparse in the space that it occupies. Sometimes, as you know, as the number of attributes will increase, we may not get values for all the attributes. In that case, it becomes sparse. So this means that there are not enough data objects to allow the creation of the model that reliably assign a class to all possible objects. So that is nothing but curves of dimensionality. You have increased the number of dimensions because of which you are not able to analyze the data properly. That is nothing but curves of dimensionality. And this is definitions of data. Density and distance between points which are critical for clustering or outlier detection, which becomes meaningful as we have, as the number of dimensions are too many. Okay. So if we have more number of dimensions, it becomes difficult to analyze the data. That is the conclusion from this. Curves of dimensionality is that only. So for this dimensionality reduction, the purpose is just to avoid this curves of dimensionality. So why this came into picture, dimensionality reduction, just to avoid this curves of dimensionality. With that, we try to reduce the amount of time as well as memory which is required by the data mining algorithms. And it also allows data to be more easily visualized, because if you have too many attributes, it's difficult to visualize the data as well. So as we reduce it, it allows us to view it easily, and also it helps you to remove irrelevant features and also to reduce noise. And what are the techniques which are applied for this dimensionality reduction? So PCA, which is principal components analysis, singular value decomposition, and others means we'll have supervised and non-linear techniques. In this chapter, you're just getting introduced to some of the terminologies which we will be discussing in detail in the further modules. Okay. So using PCA, where we are just trying to, the goal is to find a projection that captures the largest amount of variation in data. So using this PCA method, that is principal component analysis, which is one of the method.